about revising the schedule for two reasons. One reason is, and this was really the sort of the motivating reason for doing this, is on our original schedule, we would have started exponential functions day 1 this Friday, exponential functions day 2 on Monday, and then Wednesday we would have started logarithmic functions. And after asking some of you the other day if you were going to be here next Wednesday, 4 or 5 of you raised your hand. It would have been an awful end of the semester if you miss logarithmic functions. Make sure you circle this and say, do not be absent on this day. And even for those of you who would have been here on Wednesday to do logarithmic functions on Wednesday and then to pick up 5 days later on Monday when you come back from stuffing yourself with either turkey or tofurkey or whatever you eat, right? It would have just been gone from your mind. We know, right? We're not going to be doing a lot of math homework over that 5-day break. So that was really the biggest reason for doing it. And we could do it because originally when I set up this schedule, we had 2 TBA days here. And we need to keep 2 TBA days in the schedule for specifically for spring semester, because we often get at least 2 snow days. So we're always revising the schedule in the spring, which is a nightmare for me because I got to change all the dates in my math lab. So anyway, we still have that 1 TBA just in case we get a fluke like snowstorm between now and, you know, the end of the semester. All right. The other thing that students are asking about is notice that for today, there's no number for the class. We still will have 42 classes if there's no snow days. But notice today's homework would have been homework 29. That's what would be assigned to you tonight. And it would be due on Friday, right? I've gone into my math lab and I've changed the date to be Monday. So today's homework won't be due to Monday, but you can get a start on it. You'll have enough information today in class to start it, okay? So let's take a look at our preview activities for today. In fact, I only want to just discuss number 1 here because everything else will be followed with the, we'll follow it up in the class demo. So Ben, want to read this for us? Ben O? These. So if we were to label this function, which function would this be? F or G? F, right? It's the reciprocal function. So this is F and this is G. And remember, the vertical line x equals 0 is our vertical asymptote, and we always indicate our vertical asymptotes with a dashed line straight down through that x value. So the vertical asymptotes are the values that are excluded from the domain most of the time. There's a little kind of maybe sometimes it's a little different. It may not always be a vertical asymptote. We looked at that the other day briefly. It could be a whole. But to be a vertical asymptote, the x value will make your denominator 0. But not all values of x that make your denominator 0 are necessarily vertical asymptotes. And then we talked about the long-term behavior. How does our function behave when x moves towards positive infinity and negative infinity? Notice that the value of our function approaches a value. And in both of these cases, that's the horizontal asymptote, which is y equals 0. They're getting really close to 0. They're getting very close to that. And again, you could indicate that with the dashed line if you wanted. I usually just do that. I usually just do the dashed lines at the very end to remind me, but it might take some time for that graph to approach that value. It's the long-term behavior we're after. Okay. So let's start right away with a new rational function. X squared, take away 9 divided by x plus 3. Okay, so we're considering it, we're looking at it, and one of the first things we know we have to think about when we have a rational function is, where are the trouble spots? And the trouble spots are in the denominator, right? That's where we have to be concerned, because we can never have our denominator equal to 0. So x cannot be negative 3. So the value that's excluded from the domain here is x cannot be a 3. So if I asked you to write the domain for this function, you could do it in set builder notation pretty quickly like this. But on your MyMathLab homework, you know you have to put it in intervals. So it'd be negative infinity up to -3, union with -3 to positive infinity. So when I think of that domain, in my mind, I like to take out my colored pencils out of the toolkit in front of me. Well, that's what you can do. I have these famous pens up here. I just like to change the color, and I would go from negative infinity to -3 and stop at -3 and know something is going to happen there, but I'm not going to automatically put in my vertical asymptote just yet. This is just thinking about the domain of my function right now. And then from -3 to positive infinity, you know, is the rest of my domain, the two sets that make up my domain, the two infinite sets of numbers. All right. Now, this is the key. This is where you find out, is that number, is that value of x that makes my denominator 0 going to be a vertical asymptote, or will it be a straight line? And this is how you determine that. You look at your function and ask, can it be reduced? And to reduce a fraction, you always have to factor it to find the common factors of 1. So what you want to do is you want to ask yourself, to reduce this, I need to factor my numerator and my denominator. Well, in this case, my denominator is already factored, already done. It's prime. That's right. So my denominator is prime, it's x plus 3, and I like to always put my factors in parentheses. And my numerator can be factored into conjugates. Let's keep using that idea, conjugates. That means the factors look the same except for one's an addition and one's a subtraction, because it's the difference between two perfect squares. So x plus 3, and my other factor is x minus 3, which is different. It's not common. So I'll put it a different color. So notice this rational function will reduce, because I have that common factor there, to x take away 3. So suddenly I'm saying f of x is going to look like x minus 3. Whoa, baby. That thing's going to look like x minus 3? Well, almost. What picture is x minus 3? What type of graph? Linear, it's a straight line. You mean these complicated things we've been talking about and thinking about is really going to look like a straight line? Yep, except for that one trouble spot. Where x equals -3, I can put -3 in here. Look, I can put the -3 into my reduced. So this is my reduced, right? This is, if I put -3 in here, I get a value. Oops, it's -6. But -3 was what? Excluded from my domain. So right, Ian, I can't have a denominator with 0. So you always have to think about both now. You got to think about the original function and the reduced function. So -3 wasn't allowed in the original function, but in my reduced function, it would be fine. So at -3, -6, even though that point would be allowed on this line, it is not allowed on the graph of this function. So you go over to -3 and you go down to -6 and you put a hole right there at -3, -6. And then voila, you just say, okay, I just graph a straight line from here. So all you need is 2 points. So why don't, if this is my function, my reduced function x minus 3, why don't I graph my y-intercept and my x-intercept? Those are pretty easy to find. So my y-intercept is when x is 0, which is just that value, that constant value, 0, -3. So let's put that in, 0, -3, voila. And my x-intercept is when my y value is equal to 0 at +3. Right. So my x-intercept is 3, 0. So To finish this off, I just connect those points with a straight line, and voila. This is the function f of x equals x squared take away 9 divided by x plus 3. That is the graph of that rational function. It looks like a line with a hole in it. So the moral of the story is that not all values of x that make your denominator 0 automatically get put in to be vertical asymptotes. It's not an automatic movement. Many times it will be, but you have to see if that factor is common with the numerator. And if there are no common factors, then you'll know the values of x that make your denominator 0 will in fact be the vertical asymptotes. Okay. It's the only little trick on these particular functions. Any question on that before we move along? So all of what I just said is written down here for you. So that's a nice little thing to highlight, you know, later on. Make sure you have it beside you when you do your notes or when you're taking your quiz on Friday that's due Monday. It's a nice little summary to have. All right, so we have one other big idea to talk about. We sort of looked at this on Monday, but we didn't find how to find the value of our horizontal asymptote. In other words, what will y equal for my horizontal asymptote? So let's look at these three functions. I've printed out graphs of them from a graphing calculator. And the reason I kind of like the graphing calculator is as x gets closer and closer to the horizontal asymptote, the line straightens out. They don't have, I guess it doesn't have enough power in also the pixels to make them look like these little dashed lines. So if we look at this first function, what kind of conclusions can we draw about the end behavior? Remember, horizontal asymptotes is how's my function behaving when it leaves its parents, when it goes off on its own and it's very far away from the origin, right? We're very far away from the origin. So we're either a number close to positive infinity or negative infinity. So we're this huge humongous number. And if I put that huge humongous number in here for x, I want to think about, does that get really close to one specific number? So, you know, when x is small, if I put a 1 in here, I get 9 over 4, and that's 2.25. So, you know, it's kind of, you know, I don't know what that tells me, but remember, I'm not looking at numbers close to the origin. I've left my parents some way out here. So let's take a number like 100. Let's put 100 in here. Let's see what f of 100 would look like. F of 100 would be 9 times 100 squared over 3 times 100 squared plus 1. How much effect on the overall division do you think that plus 1 is going to have when x is equal to 100? It's going to have much of an effect? Not really. Well, let's take a look. I happen to have my handy dandy calculator right here. So let me put this function into my y equals. So when I put 1 in here, we saw that the answer was 2.25. So f of 1 was 2.25. If I just start increasing now by a factor of 10, let's try f of 10. F of 10 is 2.99. Because that would be like 90 over 31. 90 over 31 is pretty close to 90 divided by 30. Do you agree? Right? One's still having a little bit of an effect. But now let's go up to 100. 2.9999. So this is 2.9999. Pretty close to what number? 3. Let's try 1,000. And notice it says it's 3. Is it really 3? No. It's just that it's 2.9999, lots of 9s, and so it just rounds it to 3 because of how I have my settings in my calculator. So this particular function as x moves towards positive infinity and negative infinity, moves towards the number 3. That 1, as x gets really big, and it's getting big by squaring it in both the numerator and denominator. Notice that it's being squared in both. That little baby 1 has very little effect. So the moral of the story here is we can say that the long-term behavior of this function is that it gets really close to y equals 3. It's really close to that particular value. That's y equals 3 is the horizontal asymptote. That's the equation for it. And in symbol notation, as x approaches infinity, the value of my function approaches 3 as it approaches both positive and negative infinity. So the question of the hour is there any way I could have just looked at that function without the graph and knew right away to put in a horizontal asymptote at y equals 3? Is there any sort of like giveaways here that would be 3? What do you think from looking at this function? Nine x squared divided by 3x squared. Why I'm not paying attention to the 1 anymore, because it's almost like it's not there when these numbers are huge. That 1 has so little effect. It's like, all right, I'll give you $1 billion, or I'll give you $1,001. Are you going to be concerned about that dollar? No. Same is true here. This little constant term there is not going to have much of an effect. It's what you're doing to the big numbers. You're squaring them in both the numerator and denominator. You're doing the same exact thing. So eventually it's this ratio of 9 to 3. Because if you look at 9x squared divided by 3x squared, your x squares become 1 and you just get the number 3, because 9 divided by 3 is 3. So this little thing right here is kind of a key idea, that if the degree of your numerator is the same as the degree of your denominator, which it was in this first case, then your horizontal asymptote y equals, the number that y equals is just the division between the leading coefficient of the top and the leading coefficient of the bottom. It's the ratio of those two numbers. 9 to 3 is 3. Okay. So let's take a quick peek at our class activities here. Well, let's look at our next class demo, number 7. Just change the page there. If I asked you about the horizontal asymptote here, remember your horizontal asymptote is y equals some number, if there is one. Look at this particular one. Is this sort of behaving like the one we just looked at? Yeah, because the top is a second degree and the bottom's a second degree. So if I put in -1 million in the top and square it, and then I double it, and then I put -1 million in the bottom and square it, and there's a 1 in front of it, that little -9 has very little effect in the overall number that division represents. So what would be the horizontal asymptote here? You click off, boom, boom, my degrees are the same, so it's just 2 over 1. It's just the number 2. So right away on my graph, I could go like this. I could put that horizontal asymptote in. Notice you could draw it all the way across, but this is really the behavior of the graph way out here. So I don't bother putting that. It's just too many lines are intersecting. It gets very confusing. So I just kind of put it on the ends of my graph. All right. What about number 8? Without even covering it. Do you think my horizontal asymptote here will be 4? No. Yeah, well, look. What if x is a really big number, it's going to be even bigger in the denominator, isn't it? Because it's being squared, right? So your denominator is getting really, really big faster than your numerator. So think about what happens to a fraction. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, 1 over 9, 1 over 100, 1 over 1,000, 1 over a million. What happens to the value of that function as the denominator, of those fractions as the denominator gets really big? What happens to the value of the fraction? It gets smaller. It gets close to what? 0, right. So when your denominators, the degree of your denominator is bigger than the degree of your numerator, this thing, the denominator is getting big really fast and much faster than your numerator. So the value of your whole fraction gets really close to 0, just like your two parent functions, 1 over x and 1 over x squared. You had your x-axis as the horizontal asymptote. So here, your horizontal asymptote will be y equals 0, or your x-axis. So I just go out here, boom, 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 boom. All right, so that whole idea is back here in part A. If the degree of the numerator is less than the degree of your denominator, then y is 0 is your horizontal asymptote, your x-axis. And all you have to do is think back to the two parent functions, or take a look at this next example. 9x, instead of 9x squared now, divided by 3x squared plus 1. So I kept the denominator the same. I just made the degree of my numerator 1 instead of 2. And notice how this function is getting really close to the x-axis as it moves away from the origin. Okay, so this approaches 0. And now we have a function where our top is bigger than our bottom. The degree in our top is bigger than the degree in our bottom. We have no horizontal asymptote. None. Okay. So we're really going to be focusing in terms of our drawing of horizontal asymptotes on these two situations right here. So this is the only thing you have to remember about horizontal asymptotes. Basically, think about your parent functions, 1 over x, 1 over x squared. In both of those situations, your denominator, the degree of your denominator is bigger, and you know your x-axis was the horizontal asymptote. And when they're the same, you simply divide the coefficients, the leading coefficients, and that's it. So let's continue with this particular graph right here. I've already determined that the horizontal asymptote was 2. Where should I begin? Well, let's see what my directions tell me to do. In fact, here's some fun facts about horizontal and vertical asymptotes that you want to star and make sure you read. But in graphing, these are the steps. Notice I left something really critical out in number 1. I said make sure the rational function is fully reduced, but I didn't say and find the domain. We definitely need to find the domain, because the domain is going to help us potentially with vertical asymptotes or holes in our graph. So you want to add and find the domain to that. So let's take a look at, we'll follow those steps there, even though we threw our horizontal asymptote in so quickly here. So it says make sure our function's is fully reduced. So let's take a look at this. Well, my numerator can't be factored. It's already in factored form, 2 times x, or 2x squared. But my denominator is a subtraction problem. Those are terms. So I have to think back to my factoring, and I know that it's the difference between two perfect squares, which are these two conjugate factors, x plus 3, x minus 3. Since I see no common factors, I know I'm going to have 2 vertical asymptotes and no holes in my graph, and no holes because there's no common factors. My vertical asymptotes are at plus or minus 3. So I take out one of my colored pencils out of my little toolbox, and let's see, what do I want? I'll do a purple for -3 asymptote. So we'll go right down -3. And I always label my lines, so this will have the label x equals -3. Don't be lazy on your graphs. And x equals +3, and I go right down, straight line down. My other vertical asymptote, x equals +3. Okay, so I've reduced it. My domain is really where these vertical asymptotes, all numbers except for those vertical asymptotes. So my domain is the set of all x such that x cannot be plus or minus 3. However, I'll do this later. Right, so there we are. We've got our vertical asymptotes. We know our horizontal asymptote is 2 to 1 because we have the same degree in the top and bottom. And the two leading coefficients are 2 and 1, so we divide them, we get 2. And I got to label that line. This is y equals 2. All right, what else do I need to do? What other important information should I find? The end results, the end behaviors right here with the horizontal, yeah. What else? Would help me maybe graph this out a little bit. Intercepts, yeah. Let's take a look at the intercepts. X-intercept. And I'm going to put an S because sometimes we can have more than one. And our Y-intercept. Since our Y-axis is not a vertical, it's a Y-intercept, sorry. Since our vertical axis is not a vertical asymptote, then I can have a Y-intercept where we couldn't have one before with our parent functions. So let's see, X-intercepts, you think in your mind, you sit on the X-axis, that means your Y value is 0. So you set f of X equal to 0 and you look at your fraction. And this is when I write blah, blah, blah. Doesn't matter what the denominator is. I don't have a care in the world about the denominator because the only way my fraction could ever be a 0 is when my numerator is 0. So when is 2x squared equal to 0 when x equals what? 0. So 0, 0 is my x-intercept. And that's going to be a pretty important point. I'm going to give that a pink color right there, pink, 0, 0. And now my y-intercept, I think about where a y-intercept sits. It's on my y-axis, so my x value is 0. I don't memorize stuff, I just think about it a little bit. So let's see. F of 0 finds my y-intercept because x is 0. Is that right? No. I did that backwards, didn't I? Did I do it right? My y-intercept, are you checking me or you just kind of going, I'm doing it right? Okay. So let's do this, f of 0. So I have 2 times 0 square over 0 square minus 9, which gives me 0 over negative 9, which gives me what number? 0 divided by negative 9, 0. So both my x and y intercept is the origin. All right, you're saying, so when does the fun begin? It begins right now. Here's where the fun begins. And you probably shudder when I think it's fun, but I think, look at some of these answers, folks, in this, just for now, real quick, I'll just show it to you. Look at these graphs. When you came in here, you was probably still doing tables and maybe drawing lines and quadratics. Look at what you're going to be able to do. I think it's just amazing. You know, that's me. I think it's amazing when you can graph stuff like this. I don't know. I get excited about it. So this is the part where I just want you to take a little bit of a breath because I want to explain to you a little bit about, this is language from the book, what this means here. 7. Let's take a look at that. In fact, I'm going to take a little picture of it and put it beside our little graph here so we don't have to keep referring back to it. Let's see, this is kind of very strange language in a way. I know what it means just because I've, been working with it. Where did my picture go, I wonder? Didn't I take my picture? Well, let's try it again. I'll show. So I know this function's going to do a lot of interesting things. I got a sense of what these rational functions do. They can really move up near these asymptotes to positive infinity or down to negative infinity. I know it can hug a horizontal line when it's really far out there on the ends. I know it can cross the x-axis and the y-axis. But what I haven't figured out what to do yet is, when do I know that the function does each of those things, and how do I tell? So this is sort of a more structured way. Number 7 here helps you create a little bit of structure for taking it a piece at a time. And I'm using the word piece very consciously. It helps you piece out your domain. Right now, our domain is already slightly separated into subsets of the real number line, because we know that we can be any real number from negative infinity to negative 3. We already know that because of our domain. So right now, based on the domain, I know I could think of this subset right here from, oh, hey, yeah, look what it did to me. From negative infinity to negative 3. It's sort of like one of my intervals from negative infinity to negative 3, right? And I also know that I've got this other interval from positive 3 out to positive infinity. What role does this x-intercept play here? Well, the x-intercept takes this interval from negative 3 to 3 and it divides it into two smaller intervals. So you can think of that as two new colors now. You can think of negative 3 to 0 as one set of real numbers. And you can think of 0 to positive 3 as another set. So you can actually think about this real number line called your x-axis as being divided into 4 separate intervals. Here would be your first interval. Here would be your second. Here would be your third. And here would be your fourth. That's what number 7 tells you, but the language is really hard to understand when you first see it. Let's look at number 7. It wants us to plot at least 1 point. All right, we know what that means, but this is a language why I wanted to visually show it to you. Between each x-intercept and a vertical asymptote. So here's my x-intercept. So I'm going to pick a point somewhere between this x-intercept and this vertical asymptote. So that's one set of numbers. I'm going to pick a number out. And between this x-intercept and that vertical asymptote, I'm going to pick a value of x out and plot it. That's what that means. Plot at least 1 point between each x-intercept and a vertical asymptote. I only have one x-intercept, and I have 2 vertical asymptotes on either side. So that's intervals 2 and 3. That's the between part. And beyond each x-intercept and vertical asymptote, well, it's really beyond each, in this case, each vertical asymptote. So that would be intervals 1 and 4. All right. So that's how you chunk out your domain. You separate it into pieces. If you didn't have an x-intercept, then you would just have the intervals on either side of your vertical asymptotes. All right. Now, I'm going to erase this because I need some more room because I write so big. So I've been thinking about this for a while, and I spent a lot of time on Monday talking to you about the behavior of your 2 parent functions. I'm going to just bring those into, I'm going to take pictures of those right here that we had at the beginning. This rational function, a step by step, that's what number 7 is going to provide you here. Once you piece out the x-axis following this idea here, and that's why we have 4 different colors, you will be able to graph this. You'll also be able to graph it by just thinking about the behavior of one of your parent functions, at least this one. So let's do the more structured approach. We have 4 intervals. Everybody agree we've got 4 intervals here? So our intervals, the first interval goes from negative infinity to negative 3. The second interval goes from negative 3 to my x-intercept 0. My third interval goes from 0 to my vertical asymptote 3. And my very last interval goes beyond my vertical asymptote from 3 to infinity. So those are my 3 colored intervals. And number 7 says plot at least 1 point in each of these intervals. So let's plot a point in each of these intervals. So we just have to pick a number between negative infinity and negative 3. And in this case, since my graph only goes as far as negative 10, let's pick a number between negative 3. Well, we can't pick negative 3 because that's not allowed. But to the left of negative 3, but not bigger than negative 10. So let's just pick an x value. Would someone pick an x value there? Negative 7. So let's pick x equals negative 7 and let's find its value. So let's see, I'm looking at f of -7. So that's 2 times -7 squared over -7 squared minus 9. And guess what? You're not really going to do this because I will make sure you have a graphing calculator or a calculator. And this is where the graphing calculators are really helpful because you can put in this function, 2x quantity square divided by the quantity x square minus 9, and you can use your table to get all of these points. So let's go to my table. I'm going to set up my table, but I don't want it to do anything automatically. I want it to ask me for an x value. So let's go to my table, and I'm going to ask, hey, I said not to do that automatically. Hey, I guess I didn't click it. So enter. Okay, now let's go to my table. And I want to see the value when x is -7. So let's put -7 in and find the y value. It's 2.45. Okay, so I'm going to plot that point, 2.45. So notice I'm just above my horizontal asymptote, right? -5, -6, negative. So I'm just about right here, just a little bit above it. Right, I'm just going to plot that point there. Now let's pick a point between -3 and 0. Someone want to give me a point from table 1, a value of x from table 1 between -3 and 0? Dan? Almost between -3 and 0. Yeah, -2. So let's figure out what f of -2 is. So we put a -2 into the calculator. -1.6. Oh, interesting. I'm below the x-axis now. So at -2, I'm -1.6. I'm down here. Okay. And at 0, I already know I'm 0. And now let's pick a point. So let's throw that in here. We picked the point -2 and we got -1.6. So here we're above the x-axis. Above the x-axis. Here we're below the x-axis. All right, now one more. 0, 3. Let's pick something on the interval from 0 to 3. How about the value 2 again? All right, well, let's hope I already have this set up and I don't have to do this again. Okay, oh shoot. That's not it. Do I have 2 of these in there? Oh, I do, huh? There we go. So we'll close this one out. Exit. All right. So let's put in a 2. Any guesses? You think this is an even function? If it's even, we should get a 1.6. If it's not even, we'll get something different. Let's see. Ooh, -1.6. So at +2, we're -1.6. So when our x values are opposite, our y values are the same. This is an even function. I really should be able to stop right now because I've already got half of it that I can graph, but we'll keep going. Now a number from 3 to infinity, let's pick 7. If we pick 7, what's its x value going to be? 2.45, because that's how knowing the symmetry can help you with the graph. So that means I'll be above the x-axis. All right, I've really got all the information I need to graph this. You might be saying you're kidding. Nope. So let's see. We got a point right here. I just want to put in the 4 points I've plotted in each of those intervals. Here we go. And then I'll put the point at 7 right about there. All right. So this is how you use the concepts of horizontal and vertical asymptotes to graph this. So when I'm way out here to the left here of -10, I know that my graph is hovering really close to that horizontal asymptote. So when I go to graph this, I'm hovering. And I know I'm going to go through this point right here because I just figured that point out. That was -7, 1.6. And as I get close to this vertical asymptote, I get really bizarre and blow up to +infinity. Now, this is where the theory comes in. We already know that when you take a step to the right of -3, you're going to be negative because you plotted that point. You're in the negative. You're below the x-axis here. So that tells you that you're going to be way down here at -infinity, and you're heading towards that point because you've plotted it. And then you know you're going towards the X and Y intercept. Now this is where I just want to take a minute to see if you can think about your parent function here. This is how I just want to show you this. 2x squared over x plus 3, x minus 3. You could write, because this is a multiplication problem, it's not terms on the bottom. You could write this like this. So look at this first one, 1 over x plus 3. Parent function is 1 over x, your reciprocal function. That looks like this. Shifted left, 3. So you know the reciprocal function will change sign on either side of your asymptote. And this shows you because you've plotted a point. So all you need to think about is 1 over x plus 3 is going to act like your parent function, and you will change sign from positive infinity to negative infinity without even plotting that point. I don't even have to plot that point to know that. I'm trying to save you a little work. If you need to plot the point, it's okay. Everybody's in different spots. I can only do that because I've been doing this for years. You know, I just learned and thought about this whole idea within the last couple of semesters. I was always plotting the points and showing students, but it kind of came together for me in a way that made it a little quicker, but you don't have to worry about being quick. All right, now look, here you are. Let's suppose you didn't plot this point. You only have 2 choices from here. You can continue towards that vertical asymptote and go up to positive infinity like that, or you could come down. And this is really where you need to know what the sign of your graph is on this interval. So that point helps you to determine that this bounces at 0, 0. Look at that, x squared bounces and comes back down. So with a little bit more knowledge, you could see that that couldn't go up because of the x squared there. All right, now, what do? This asymptote comes from this factor, 1 over x minus 3. That factor has a 1 there. It's going to be like 1 over x. It's going to act like an odd multiplicity. Odd multiplicities with a 1 acts like a straight line. It changes sign when it crosses, when it's a polynomial function. And now this acts like 1 over x moved to the right 3. I know my sign will change. In my parent function 1 over x, my sign changes when I take a step on the other side of 3. So, and you also know you've got to be up here at positive infinity because you plotted that point right there. There's no way you could be down here, folks. Look, because if you were down here, to get to that horizontal asymptote, you would have to cross the x-axis, and you can't cross the x-axis because your only x-intercept is right there. You have no choice but to be above and then come down and hug this forever and ever. Okay, so we're above, you come down, you hit that point you plotted, doesn't really matter, and you hug. And voila, there is 2x squared divided by x squared minus 9. A lot. There's a tremendous amount of knowledge in graphing these. I recognize that. It's going to take you a long time. You'll have 20 minutes today to work on your class activities and the entire class on Friday. Please, it's so tempting to not work through some of the steps and just take a quick peek at the answers in the back. You're going to be cheating yourself a little bit. If you want, I'll come and look at it and say, yep, and then you can just move on without looking at the answers. But I'm just giving you that as a suggestion. Okay, I'm not even going to do number 8 for you because I think you're on your way. And it's really, you've listened to me enough today. So again, you have 9 rational functions to graph, and you have 20 minutes today and another 110 minutes on Friday. Put up your flags if you have any questions.